Okay, so in this part, we're going to prove what is actually a sort of famous theorem from real analysis, intro real analysis classes, which is about monotonic subsequences. So the theorem basically says that every sequence has a monotonic subsequence. So it's a very kind of a powerful general statement, and it's kind of notoriously tricky to prove. So I'm going to do my best, because what the book does, the book's proof of this is very slick. So it's very short and simple, and it is easy to understand, but it's not that easy to see where the ideas came from. So I kind of, I'll try to motivate it just a little bit here. Okay. So let's let Sn be a sequence. Right. Suppose we try to pick S and K to be increasing. Okay, so suppose we're trying to pick an increasing subsequence of Sn, right? Naively, we do this. Okay, so we might try to do something like this. Pick S1, pick S2, or sorry, not S1, Sn1, and 2 bigger than Sn1, right? This is the most obvious thing we could try to do. Right? But this could fail, right? Why? If some Snk is greater than Sm for all m greater than nk. So if we accidentally hit a term which is actually bigger than everything that comes after it in the sequence, then we're dead, right? We can't continue picking things that are bigger than what we've picked so far. And sometimes actually some of the earlier choices, could force us into this situation. Namely, if we pick any term for which only finitely many terms that come later are bigger than the term we picked, then we have a problem. Okay, so how to avoid this? All right. So for one thing, this is what the book calls a dominant term. And we'll return to that in a second. So we accidentally picked a dominant term. We want to avoid all the dominant terms. As long as we can avoid all dominant terms or anything that like leads us to a dominant term, then we'd be safe, right? So how to avoid this? Well, pick N1 big enough so that all the dominant terms, so all the terms which are bigger than everything that comes after them, all dominant terms are before N1. However, this is only possible if there are finitely many dominant terms. Whoops. Oh, didn't mean to do that. Oh, I see. I can make pages like this. Okay, cool. So, all right. Right. So, Right. So what I was just saying is that if we picked our first term in our subsequence to be after all the dominant terms, then we would be fine. We would be safe. We could just keep doing this process. However, that's only possible if there are only finitely many dominant terms. So some sequences might actually have infinitely many dominant terms. And in those sequences, there might be no increasing subsequences. There might be no monotonically increasing subsequences. But in those sequences, the fact that there are infinitely many dominant terms ends up guaranteeing that there is a monotonically decreasing subsequence. So that's basically the structure of the proof here. So yeah, I am going to erase this. I'll make a cut. Okay, so let's prove this theorem now. So like I was saying before, right, if there are only finitely many dominant terms, we know we can find an increasing subsequence. If there are infinitely many dominant terms, we know we can find a decreasing subsequence. Just to remind you, what I mean by dominant, okay, is so call M, or actually, let's see, N, sorry, N, which is an index actually, right? Not a value of Sn, but just an index. So say this is dominant if Sm is less than Sn for m greater than n. So basically, n is dominant if Sn is bigger than every term that comes after it in the sequence, okay? So case 1, there are infinitely many dominant n, right? So if there are infinitely many dominant values of n, then take nk such that nk is dominant for each k. So we can just find an infinite sequence where all of the terms are dominant, right? Because there are infinitely many values that are dominant, we can just find an infinite subsequence of them, and that has to be a decreasing sequence. Let's say, you know, Snk plus 1 is less than Snk for all k, since Nk is dominant, right? So that's the decreasing subsequence case. So we can find a decreasing subsequence in this case, and we can find an increasing subsequence in the other case. I'm going to erase this case. So case 2 is there are only finitely many dominant n. So in this case, then take n1 greater than all dominant values of n, right? So we choose the first term of the subsequence to be after all of the dominant ones. Then Sn1 is not dominant. So there exists an n2, such, you know, n2, sorry, greater than n1, such that Sn2 is greater than Sn1, right? Because Sn1, like not Sn1, n1 is not dominant. Oh yeah, this is not quite the right terminology. So n1 is not dominant. So we have to be able to find something which is bigger than it later on. Then N2 is also not dominant. So there exists an N3 greater than N2 such that Sn3 is greater than Sn2. Right? Just continue this process. Because we're already past all the dominant terms, we can always keep finding terms which are bigger than the last one that we chose, and we can just build an infinite subsequence that way, okay? So that shows that every sequence has a monotonic subsequence. Great. So that's a very powerful theorem, by the way. It's very useful. And there's one more statement I would like to make, which is just sort of an elegant or sort of a, you know, nice encapsulation of some of the stuff that we've done so far. And it has a name, actually, which is the Bolzano-Weierstrass theorem. So I want to just state that now. So this is theorem 11.5. Every bounded sequence has a convergent subsequence. This is, well, so just to sort of round this out, the proof is very short. Let Sn be bounded. Then there exists a monotonic subsequence Snk. Then Snk is convergent by 10.2, I think. Yep, because it's bounded and monotone. So that's the proof here. This statement really is kind of it ends up being sort of a fundamental statement about something about the topological properties of R, because another way, so for anyone who knows anything about topology, and don't worry, this is like totally just flavor for now, although we will talk about topology later. But for now, you don't have to worry too much about it. But this ends up being basically the same as saying that closed intervals are compact in R. Okay, so don't, you know, if you don't know what this means, that's completely fine. We'll return to it later. Okay, so that does it for this video. See you in the next one.